Tonight, I want you to picture something amazing. Imagine drifting in the endless dark of space, surrounded by a glowing river of stars. That river is our home, the Milky Way, and we're about to take a journey straight into its heart here at Boring Science Channel. We'll travel from our quiet solar system, past star-forming regions, through clusters older than time itself, and all the way to the most powerful force in our galaxy, the supermassive black hole that holds it all together. Along the way, we'll uncover how the Milky Way got its shape, why its spiral arms last for billions of years, and what hidden forces sculpt the universe around us. We'll see newborn stars, ancient giants, and cosmic neighborhoods so bright that night would never fall. But this isn't just about space, it's about time. Looking into the center of our galaxy means looking back through history at the events that created not just stars and planets, but the very atoms in our bodies. So let's begin. Let's dive into the center of the Milky Way. The visuals are here if you want them, but you can also just close your eyes, breathe, and drift into the stars with me. And hey, tell me where you're tuning in from tonight. Drop your time and location in the comments. I'd love to see. If you find comfort in these starlit explorations, I'd be truly grateful if you'd give this video a gentle like and consider subscribing. It helps other curious souls discover this peaceful corner of the cosmos, and it means I can continue crafting these soothing journeys for you. Now, I do hope this won't be too fascinating and keep you awake. Though if it does, at least you'll drift off with your mind full of stellar wonders. So settle back, close your eyes if you wish, and let's embark on what might be the most incredible voyage you've ever imagined. Tonight, we're going to travel together from our quiet suburban corner of the cosmos all the way to the beating heart of our galactic home. Picture yourself floating weightlessly through the infinite darkness, surrounded by rivers of starlight that stretch across unimaginable distances. We're going to journey inward through neighborhoods of stars, past cosmic nurseries where new suns are born, through regions where ancient stellar giants remember the galaxy's youth, until we reach the most mysterious and powerful place in our entire cosmic neighborhood. It's a journey that spans not just incredible distances, but incredible mysteries. We'll discover why our galaxy spirals in such elegant curves, how stellar explosions sculpt the very architecture of space, and what forces have been quietly shaping our cosmic home for over 13 billion years. Most remarkably, this journey through space is also a journey through time itself, because every step inward takes us deeper into the story of how simple hydrogen became complex enough to dream, to wonder, and to contemplate the very stars from which it came. Let's begin this gentle descent into the magnificent structure we call the Milky Way. Our journey starts exactly where you are right now, here on Earth, orbiting our familiar yellow sun in what astronomers call the local bubble. We're not floating randomly through the cosmos, but residing in a very specific address in our galactic neighborhood, positioned roughly 26,000 light years from the center of our galaxy. To help you picture our location, imagine if the entire Milky Way were shrunk down to the size of a large city. We'd be living in a comfortable suburb, not quite downtown where the action gets intense, but certainly not out in the rural outskirts either. We're in that sweet spot where stars are spaced at reasonable distances, where the cosmic weather stays relatively mild, and where complex chemistry has had the time and stability it needs to evolve into something as remarkable as consciousness itself. This isn't just a random address we've ended up in. Our location represents something precious in galactic terms: stability. You see, our galaxy is a dynamic, ever-changing system where stellar explosions, gravitational chaos, and intense radiation can make vast regions utterly hostile to the delicate processes that allow life to flourish. But here in what scientists call the galactic habitable zone, conditions have remained steady enough for billions of years that atoms could organize themselves into molecules, molecules into cells, and cells into beings capable of contemplating their own cosmic origins. From our vantage point, The galaxy appears as that familiar band of light stretching across our night sky on clear, dark evenings. Ancient peoples looked up at this celestial river and gave it names that reflected their wonder. The Greeks called it Galaxias, meaning milky, from which we get our modern name. Romans knew it as Via Lactea, the Milky Road. Indigenous cultures around the world saw it as a pathway for spirits, a cosmic river, or the backbone of night itself. They were all describing the same magnificent structure we're about to explore from the inside. But what exactly are we seeing when we gaze up at that soft glow of starlight? We're looking at our galaxy edge on, like viewing a dinner plate from the side. The Milky Way is what astronomers classify as a barred spiral galaxy, stretching roughly 100,000 light-years from edge to edge and containing somewhere between 200 and 400 billion stars. That's more stars than there are grains of sand on all the beaches of Earth, all held together in an elegant gravitational dance that's been ongoing for over 13 billion years. The structure we're embedded within isn't random or chaotic. Our galaxy has a distinct architecture, like a cosmic city with different districts, each with its own character and population. There's the thin disk where we live, populated by younger stars, gas and dust, still actively participating in the ongoing story of stellar birth and death. Above and below us stretches the thick disk, home to older stellar populations that remember when the galaxy was young and the universe contained far fewer heavy elements. Surrounding everything is the galactic halo, a roughly spherical region containing the galaxy's most ancient stars, arranged in beautiful globular clusters that orbit like satellites around the main galactic structure. These stellar cities are time capsules, preserving within their populations the conditions that existed when the galaxy first began to take shape from the primordial hydrogen that filled the early universe. Threading through it all are the spiral arms, those graceful curves that give our galaxy its distinctive pinwheel appearance. But here's something fascinating. These aren't fixed structures like the spokes of a wheel. They're density waves, patterns that sweep around the galaxy like cosmic traffic jams, compressing gas and triggering star formation as they pass. Imagine ocean waves rolling toward shore, except these waves are made of gravity itself, sculpting the distribution of matter as they propagate through the galactic disk. As we prepare to leave our comfortable neighborhood and venture inward, it's worth appreciating just how perfectly positioned we are to observe the universe. We're far enough from the galactic center to avoid the intense radiation and gravitational chaos found there, yet close enough to the galactic plane to witness the full glory of stellar evolution in action. We exist in a region where heavy elements forged in previous generations of stars have enriched the local environment, making rocky planets and the complex chemistry of life possible. Our Sun completes its orbit around the galactic center roughly once every 225 million years. This is called a galactic year, and Earth has completed about 20 of these cosmic orbits since complex life first emerged in our oceans. During our last galactic year, dinosaurs ruled the Earth. The next time we complete this vast circuit, our Sun will be noticeably older, and if humans still exist, we'll have witnessed cosmic changes we can barely imagine today. But tonight, we're not content to simply orbit peacefully in our suburban solar system. We're going to travel inward, through regions where the stellar density increases dramatically, where gravitational forces grow stronger, and where the very nature of space and time begins to behave in ways that challenge our everyday understanding of reality. The first leg of our journey takes us through what astronomers call the local arm, sometimes known as the Orion arm. This is the spiral arm segment where our solar system currently resides. It's considered a relatively minor arm compared to the galaxy's grand design, more of a spur connecting the larger Perseus and Sagittarius arms than a major feature in its own right. But minor doesn't mean insignificant. This region contains some of the most beautiful and scientifically important objects in our local galactic neighborhood. As we travel inward from our solar system, we encounter the diverse stellar population that makes up our cosmic community. Within just a few dozen light years of Earth, we find red dwarf stars that will burn steadily for trillions of years. Massive blue giants that live fast and die young in spectacular fashion, and white dwarf stars that represent the final fate awaiting stars like our own sun. Each of these stellar types tells us something profound about the life cycle of matter in our galaxy and the processes that have been shaping cosmic evolution since the universe began. The red dwarfs, small and dim but incredibly long-lived, will still be shining when our sun has long since exhausted its fuel. The blue giants, blazing with the luminosity of thousands of suns, will burn through their nuclear fuel in just a few million years before ending their lives in catastrophic supernova explosions that scatter heavy elements throughout their neighborhood. One of the most striking features we encounter as we move inward is something called the Gould Belt, a ring of young hot stars and star-forming regions that surrounds our solar system like a cosmic wreath. This structure, named after astronomer Benjamin Gould, who first mapped it in the 1870s, represents a relatively recent burst of star formation in our galactic neighborhood. The belt is tilted about 20 degrees relative to the galactic plane and contains many of the bright stars and colorful nebulae visible to the naked eye from Earth. Within the Gould Belt, we find stellar nurseries where new stars are being born at this very moment. The Orion Nebula, visible as the sword hanging from the constellation Orion, is perhaps the most famous of these cosmic maternity wards. Here, dense clouds of gas and dust are collapsing under their own gravity, heating up as they contract until they reach the critical temperature and pressure needed to ignite the nuclear fusion reactions that will power a star for billions of years. But star formation isn't a gentle, quiet process. It's violent, chaotic, and breathtakingly beautiful. As massive stars form, they emit intense stellar winds that blow away surrounding material like cosmic hurricanes, creating vast cavities in the interstellar medium. When these massive stars reach the end of their brief but brilliant lives, they explode as supernovae, sending shock waves rippling through space that can trigger new rounds of star formation while simultaneously enriching the local environment with the heavy elements forged in their cores. These stellar explosions have profoundly shaped our local galactic environment. We exist within what's called the local bubble, a region of space that's been swept relatively clean of dust and gas by ancient supernova explosions. This bubble extends for several hundred light years in all directions and gives us an unusually clear view of the cosmos beyond. Without this cosmic clearing, our night sky would be much dustier, and our ability to study distant galaxies would be severely compromised. As we continue our journey inward, something subtle but significant begins to change. The stellar density starts to increase. What began as a leisurely cruise through the galactic suburbs gradually transforms into a voyage through more crowded stellar neighborhoods. The average distance between stars decreases from the 4.3 light years that separate us from our nearest stellar neighbor, Alpha Centauri, to distances measured in single light years or even less. This increasing stellar density carries profound implications for planetary systems and the potential for life. In regions where stars are closely packed, gravitational interactions become more frequent and more dramatic. Planetary orbits that would remain stable for billions of years in our quiet neighborhood might be disrupted by passing stars in these denser regions. Close stellar encounters could strip planets from their host stars entirely, or send comets and asteroids careening through inner planetary systems in catastrophic bombardments. Yet this increasing density also brings remarkable opportunities for observation and discovery. The probability of witnessing spectacular astronomical events increases dramatically as we venture deeper into the galaxy. Stellar collisions, though still extraordinarily rare, become possible. Binary star systems where two stars orbit each other in intricate gravitational dances become increasingly common. The sheer variety of stellar types and evolutionary stages creates a cosmic laboratory where we can observe phenomena that simply don't occur in our peaceful local neighborhood. Our inward journey also reveals how the interstellar medium, the material that fills the space between stars, begins to transform in fascinating ways. What we often think of as empty space is actually filled with gas, dust, magnetic fields, and various forms of radiation. In our local neighborhood, this material is relatively sparse, cleared out by those ancient stellar explosions we mentioned. But as we move toward the galactic center, the density of interstellar material increases dramatically, creating an environment rich with the raw ingredients for future star and planet formation. The dust grains floating through this cosmic medium aren't just debris left over from stellar destruction. They're the building blocks of worlds yet to be born. These tiny particles, typically smaller than the smoke from a candle, are forged in the cooling atmospheres of dying stars and scattered throughout the galaxy by stellar winds and explosive deaths. Each grain carries within it the chemical legacy of previous stellar generations, including the carbon, oxygen, silicon, and iron that will eventually become incorporated into new planets, new moons, and perhaps even new forms of life. The magnetic fields threading through this material create invisible highways that guide the flow of matter through the galaxy. Though incredibly weak by earthly standards, these fields extend across vast distances and help channel material into the spiral arms where it can participate in fresh episodes of star formation. They also accelerate charged particles to tremendous energies, creating the cosmic rays that constantly rain down on our solar system and every other stellar neighborhood throughout the galaxy. As we venture deeper into the Milky Way's embrace, we begin to encounter the galaxy's spiral arms in earnest. These aren't permanent fixtures carved into space, but rather waves of enhanced density that sweep around the galactic disk like ripples on a cosmic pond. When the natural rhythm of gas movement inside a region aligns with the timing of an approaching density wave, the effects stack upon each other, creating spectacular displays of stellar birth that illuminate entire spiral arms with their brilliance. The spiral arms represent some of the most dynamic and energetic regions in our entire galaxy. Here, the interstellar medium gets compressed to densities high enough that gravity can overcome the outward pressure of heated gas, triggering the collapse that leads to star formation. The newly formed massive stars bathe their surroundings in intense ultraviolet radiation, creating those magnificent glowing nebulae that trace out the spiral pattern visible in photographs of distant galaxies. But these regions of stellar nurseries are also cosmic graveyards. The most massive stars burn through their nuclear fuel reserves in just a few million years before exploding as supernovae. These titanic explosions inject enormous quantities of energy into their surroundings, heating the interstellar medium to millions of degrees, accelerating cosmic rays to nearly the speed of light, and triggering shock waves that can either encourage or suppress further star formation depending on local conditions. This delicate interplay between stellar birth and stellar death creates a complex ecosystem where matter constantly cycles between the interstellar medium and stellar interiors. With each cycle, new heavy elements get added to the galactic chemical inventory through a process astronomers call galactic chemical evolution. This cosmic recycling program has been operating for over 13 billion years and is directly responsible for creating the rich variety of elements that make rocky planets and complex chemistry possible. Picture yourself drifting through one of these spiral arms, surrounded by the soft glow of star-forming regions stretching across hundreds of light years. Massive molecular clouds, some containing the mass of 1 million suns, float through space like cosmic icebergs, their interiors so cold that molecules freeze onto dust grains, building up icy mantles of water, methane, and ammonia. These clouds represent some of the most pristine material in the galaxy, gas that has been enriched by countless generations of stellar evolution but is now gathering into dense concentrations where gravity can begin its patient work of building new solar systems. The process unfolds with majestic slowness. It can take millions of years for a molecular cloud to contract enough for star formation to commence. But when it finally does, the results are nothing short of spectacular. Within a single star-forming complex, dozens or even hundreds of new stars can ignite simultaneously, creating stellar associations that will gradually drift apart as they orbit the galactic center. As our journey carries us through these bustling cosmic neighborhoods, we witness how the chemical composition of space itself has evolved over time. The interstellar medium here is enriched with elements that simply didn't exist when the galaxy was young. Oxygen, carbon, nitrogen, silicon, iron, and dozens of other elements are mixed into the gas and dust like ingredients in a cosmic recipe, the products of nuclear fusion reactions that occurred in stellar cores over billions of years. This chemical enrichment represents one of the most important processes in the entire history of the universe. When the cosmos was young, shortly after the Big Bang, it contained only hydrogen and helium with trace amounts of lithium. Everything else, every element heavier than helium that makes up rocky planets, organic molecules, and our own bodies, had to be manufactured inside stars and distributed through space by stellar winds and explosive deaths. The spiral arms serve as both the factories and distribution centers for this ongoing chemical evolution. Here, massive stars live their brief but brilliant lives, fusing lighter elements into heavier ones deep within their cores. When these stellar giants explode, they don't just release tremendous amounts of energy. They release the periodic table itself, sending newly minted elements racing through space at thousands of kilometers per second. These supernova shockwaves accomplish more than just scattering heavy elements throughout the galaxy. They also compress surrounding interstellar material, triggering fresh rounds of star formation in an endless cycle where stellar death enables stellar birth. Each new generation of stars forms from material that's slightly more metal-rich than the last, a gradual process of cosmic enrichment that has been building complexity into the universe atom by atom, star by star, for eons. The spiral arms themselves aren't permanent features frozen into the galactic structure. They rotate around the galactic center at a different speed than the stars, creating a pattern that persists even as individual stars and gas clouds move in and out of the spiral framework. Our own solar system has passed through several spiral arms during its 4.5 billion year history, experiencing periods of enhanced star formation and increased supernova activity during these transits. Some researchers believe these passages through spiral arms may have influenced the evolution of life on Earth itself. The increased flux of cosmic rays from nearby supernova explosions could have caused genetic mutations, potentially accelerating evolutionary change during certain geological epochs. The enhanced star formation could have created more massive stars in our cosmic neighborhood, leading to spectacular supernova displays that ancient organisms might have witnessed blazing across their skies. As we continue our inward voyage, the stellar population around us begins to shift in subtle but meaningful ways. Stars become, on average, more massive and more luminous than those in our home neighborhood. The proportion of binary and multiple star systems increases, and we begin to encounter stellar types that are rare or completely absent in our quiet galactic suburb. Wolf-Rayet stars represent one of the most extreme phases of stellar evolution we encounter on this journey. These objects have stripped away their outer hydrogen layers, exposing their helium-burning cores directly to space. They shine with the luminosity of hundreds of thousands of suns and drive stellar winds so powerful they can excavate cavities dozens of light years across in the surrounding medium. These are stars racing through their final evolutionary stages, consuming their nuclear fuel at prodigious rates before ending their lives in some of the most energetic explosions the universe can produce. The presence of these exotic stellar types creates a more dynamic and potentially hazardous galactic environment. The intense ultraviolet radiation from massive stars can sterilize planetary surfaces across interstellar distances. Stellar winds and supernova shock waves can strip away planetary atmospheres or trigger massive climate changes on worlds orbiting nearby stars. Yet this same harsh environment proves incredibly fertile for creating complex chemistry, as intense radiation fields and energetic particles drive chemical reactions impossible under gentler conditions. As we penetrate deeper into the galaxy's spiral structure, we also begin to sense the effects of something that has been subtly influencing our journey all along. Even from thousands of light years away, we can detect the gravitational influence of our ultimate destination in the orbital motions of stars, in the flow patterns of interstellar gas, and in the overall architecture of the galactic disk itself. This is the supermassive black hole that anchors our entire galaxy, containing the mass of over 4 million suns compressed into a region smaller than our solar system. It's a gravitational monster that warps the fabric of space-time around it, creating conditions so extreme they serve as natural laboratories for testing our most fundamental theories about the nature of reality itself. But reaching this cosmic heart will require us to traverse even more extraordinary environments, regions where stellar densities climb thousands of times higher than anything in our local neighborhood, where the interstellar medium gets heated to temperatures of millions of degrees, and where the normal rules of physics get stretched to their absolute limits. The adventure ahead promises wonders that will challenge our understanding of space, time, and the very nature of existence itself. Our destination lies ahead, but between us and that cosmic heart stretches one of the most remarkable regions in our entire galaxy. As we drift deeper through the spiral arms, something extraordinary begins to unfold around us. The stellar neighborhoods we've grown familiar with start giving way to something far more ancient, far more densely populated, and infinitely more mysterious. We're approaching what astronomers call the galactic bulge, that central swelling of our galaxy where 10 billion years of cosmic history have compressed into a region that challenges everything we thought we knew about stellar evolution. The transition isn't sudden or jarring. It's more like watching a quiet suburban landscape gradually transform into the bustling heart of an ancient city. The spaces between stars, which once stretched for light years, now shrink to distances that would fit comfortably within our own solar system. Where we once encountered perhaps one star every few cubic light years, we now find ourselves surrounded by stellar densities that would make our night sky appear as bright as twilight if we could somehow transport Earth to these regions. The darkness between stars becomes a rare commodity here, replaced by the gentle glow of countless distant suns. But it's not merely the density that transforms as we venture inward. The very character of the stars around us tells a story of deep cosmic time. These are the galaxy's elders, ancient red giants and evolved stars that formed when our Milky Way was young and the universe contained far fewer of the heavy elements we take for granted today. Their reddish glow speaks of ages measured not in millions but in billions of years, of stellar lives that began when the first complex galaxies were still taking shape across the cosmos. Here in the galactic bulge, we encounter what astronomers classify as population 2 stars. Unlike the metal-rich population 1 stars of the spiral arms, these ancient suns formed from gas that had been enriched by only the first few generations of stellar death and rebirth. Their atmospheres contain less iron, fewer heavy elements, and their light carries the chemical signature of a younger, simpler universe when hydrogen and helium dominated the cosmic recipe. The architecture of space itself becomes more intricate as we penetrate deeper into this region. The orderly spiral structure that has guided our journey thus far begins to dissolve into something more complex, more three-dimensional. Stars move in elongated orbits that carry them high above and below the galactic plane, creating a roughly spherical distribution that extends thousands of light years in all directions from the galactic center. This isn't chaotic motion, but rather the result of billions of years of gravitational choreography. These orbital patterns were sculpted by countless stellar encounters, by the slow but inexorable influence of our destination black hole, and by the complex interplay between visible matter and the invisible dark matter that provides the gravitational scaffolding for our entire galaxy. Each star follows a trajectory that was set in motion when the galaxy was young, and their collective dance creates the bulging, elliptical structure that dominates the inner regions of the Milky Way. As we drift deeper into this ancient stellar realm, we begin encountering some of the most extraordinary objects in our galaxy. Globular clusters become increasingly common, those perfect spheres of stars that shine like cosmic chandeliers suspended in the galactic halo. Each cluster contains hundreds of thousands of stars packed into a region just a few dozen light years across, creating stellar densities so extreme that the night sky from within such a cluster would blaze with thousands of stars brighter than Venus appears from Earth. These globular clusters are cosmic time capsules, preserving within their stellar populations the conditions that existed when our galaxy first began to coalesce from the primordial hydrogen that filled the early universe. The stars within them formed almost simultaneously from the same ancient gas cloud, and they've been orbiting together ever since, slowly evolving but maintaining their gravitational embrace across cosmic time. By studying their colors, brightness, and chemical composition, astronomers can read the story of galactic youth written in starlight. But globular clusters reveal something else remarkable, something that hints at the violent processes that shaped the galactic bulge. Many of these stellar cities show evidence of multiple generations of star formation, with different populations exhibiting varying chemical compositions and ages. This complexity suggests that the central regions of our galaxy weren't assembled through a single gradual process, but rather through multiple episodes of stellar formation, galactic collisions, and the accretion of smaller satellite galaxies. The evidence for this tumultuous past becomes more apparent as we examine the motions of stars around us. Unlike the orderly rotation of the galactic disk, stars in the bulge move in complex, highly elliptical orbits that carry them on intricate three-dimensional paths around the galactic center. Some stars plunge deep toward the central black hole before swinging back out to the bulge's edge. Others follow box-like trajectories that never bring them close to the galactic plane. These orbital patterns preserve the memory of ancient gravitational encounters. When galaxies collide and merge, their stellar populations don't simply blend together smoothly. Instead, gravitational forces stretch and distort the original orbital structure, creating the kind of complex three-dimensional stellar distribution we observe in the galactic bulge. The stars surrounding us are the surviving remnants of these ancient cosmic catastrophes, their motions forever encoding the violent history of galactic assembly. Yet the bulge isn't merely a museum of ancient stellar populations. It's also a region of ongoing stellar drama, where the intense gravitational environment creates phenomena that occur nowhere else in our galaxy. The high stellar densities lead to frequent close encounters between stars, sometimes resulting in stellar collisions or the formation of exotic binary systems where two stars orbit each other at distances closer than the diameter of our Sun. These close stellar encounters can have profound consequences. When two main sequence stars collide, they can merge into a single, more massive object that appears younger and bluer than the surrounding stellar population. These blue stragglers stand out like cosmic anachronisms, seemingly having reversed the aging process through the violence of their formation. The dense stellar environment also creates opportunities for the formation of some of the most exotic objects in the universe. Neutron stars, the collapsed cores of massive stars that have undergone supernova explosions, become more common in these regions. Some of these neutron stars get spun up to incredible rotation rates by accreting material from companion stars, becoming millisecond pulsars that sweep beams of radiation across space with clockwork precision. X-ray sources become increasingly common as we move deeper into the bulge, marking locations where matter falls onto compact objects like neutron stars and black holes. The intense gravitational fields around these objects heat infalling material to temperatures of millions of degrees, causing it to emit high-energy radiation that can be detected by space-based telescopes across the galaxy. But perhaps most significantly, we begin to sense the influence of something far more massive than any individual star or stellar remnant. Our ultimate destination, still thousands of light years away, begins to make its presence felt through subtle but measurable effects on the motions of stars and gas throughout the galactic bulge. This gravitational influence manifests in several ways. The overall rotation curve of the galaxy shows clear evidence of a central mass concentration. Gas flows in the inner galaxy are channeled by gravitational forces that can only be explained by the presence of a supermassive black hole. And the orbits of individual stars, particularly those closest to the galactic center, show the unmistakable signature of motion in an extremely strong gravitational field. The interstellar medium in the galactic bulge transforms dramatically from anything we encountered in the spiral arms. Here, the space between stars fills with hot, ionized gas heated by the collective radiation from millions of evolved stars. Temperatures reach millions of degrees, creating a tenuous but extensive atmosphere of hot plasma that permeates the entire bulge region. This hot gas doesn't remain static. It flows, driven by pressure gradients, magnetic fields, and the gravitational pull of the central black hole. Streams of material fall inward along complex trajectories, sometimes forming temporary ring structures or spiral patterns as they respond to the gravitational forces that thread through the galactic center. The magnetic environment itself becomes increasingly complex as we approach our destination. The magnetic field lines, which in the spiral arms generally followed the spiral structure, become twisted and distorted by the intricate motions of gas and the influence of the central black hole. These magnetic fields channel the flow of cosmic rays, trap hot gas in magnetic loops, and accelerate charged particles to incredible energies. As we continue our inward journey, something subtle but profound begins to change in the very nature of space and time around us. The intense gravitational field of the central black hole, though still distant, creates relativistic effects that become increasingly important. Time runs slightly slower than it would in our galactic suburbs. Light becomes gravitationally redshifted as it climbs out of the deepening gravitational well, and the paths of particles, whether they're photons of light or cosmic ray nuclei, begin to curve noticeably as they respond to the warped geometry of space-time itself. The stellar populations continue to evolve as we venture deeper into the bulge. We encounter more stars in advanced stages of evolution, red giants that have swollen to enormous sizes as they exhaust the hydrogen fuel in their cores, white dwarf stars, the hot, dense remnants of stars like our Sun that have shed their outer layers and settled into their final cooling phase. Increasingly, we find evidence of stellar populations that have been stirred and mixed by the complex gravitational environment. Some regions of the bulge show evidence of more recent star formation, suggesting that the supply of gas for making new stars hasn't been completely exhausted despite the ancient age of most bulge stars. These younger stellar populations create a layered structure where stars of different ages and chemical compositions coexist in the same region of space. The dust that we encountered abundantly in the spiral arms becomes increasingly scarce as we move deeper into the bulge. The hot, ionized gas and intense radiation fields strip away or destroy much of the fine cosmic dust that serves as raw material for planet formation in the outer galaxy. What dust remains tends to be concentrated in dense clouds that have somehow managed to survive in this harsh environment. This scarcity of dust carries profound implications for planetary system formation in the galactic bulge. While planets can and do form around bulge stars, they're likely to be primarily gas giants and rocky worlds with compositions quite different from the planets in our solar system. The reduced abundance of heavy elements and the scarcity of dust make it less likely that Earth-like worlds could form and maintain stable, habitable conditions over geological time. Yet even in this seemingly hostile environment, we find evidence of complex chemistry and molecular formation. Radio telescopes have detected various molecular species in the dense gas clouds of the galactic bulge, including some of the same organic molecules found in star-forming regions throughout the galaxy. The chemistry of life, it seems, finds ways to operate even in the most extreme galactic environments. As our journey carries us ever deeper into the heart of our galaxy, we begin to sense that we're approaching something truly extraordinary. The gravitational field grows stronger with each passing light year. Stellar motions become more extreme, with stars moving at velocities that would carry them completely out of the galaxy if they weren't bound by the intense gravitational embrace of what lies ahead. Radio and X-ray emissions from the galactic center grow stronger, signaling the presence of high-energy processes operating on scales and at intensities that dwarf anything we've encountered so far. We're approaching a region where the familiar rules of stellar physics give way to something far more exotic, where matter and energy interact in ways that push the boundaries of our understanding. The supermassive black hole that anchors our galaxy still lies ahead, but its influence has become unmistakable. We can sense it in the orbital motions of nearby stars, in the flow patterns of interstellar gas, and in the high-energy radiation that escapes from the immediate vicinity of the event horizon. We're approaching the most extreme gravitational environment in our galaxy, where the curvature of space-time becomes so severe that it fundamentally alters the nature of reality itself. But before we can reach that ultimate destination, we must traverse the final regions of the galactic bulge, where stellar densities reach their maximum, where the most exotic stellar populations reside, and where the interplay between gravity, magnetism, and high-energy physics creates phenomena that exist nowhere else in the known universe. The center of the Milky Way beckons with mysteries that will challenge everything we think we know about black holes, gravity, and the fundamental nature of space and time. Our journey is approaching its most spectacular and mind-bending phase, where science meets the truly sublime, and where the universe reveals some of its deepest secrets to those patient enough to venture into the beating heart of our cosmic home. As we penetrate the final layers of the galactic bulge, something remarkable begins to unfold around us. The stellar environment transforms into something that challenges our most basic understanding of cosmic architecture. Stars that once seemed densely packed now appear almost sparse compared to what lies ahead. We're approaching what astronomers call the nuclear bulge, the innermost region of our galaxy, where stellar densities reach values that would have seemed impossible just a few thousand light years ago. Here, within a few hundred light years of the galactic center, we encounter stellar populations so tightly packed that the average distance between stars shrinks to less than a single light year. If Earth existed in this environment, our night sky would blaze with thousands of stars brighter than the full moon. creating a perpetual twilight that would make true darkness impossible. The gravitational interactions between these closely packed stars create a dynamic, ever-changing stellar ballet, where close encounters and orbital perturbations are not rare events, but routine occurrences that constantly reshape the stellar landscape. The stars themselves tell an even more remarkable story. These aren't just ancient population 2 stars, but representatives of some of the most extreme stellar evolution pathways in the universe. We encounter massive red supergiants that have swollen to sizes larger than Earth's entire orbit around the Sun. Their surfaces so cool they glow with deep crimson light, yet so luminous they outshine entire star clusters. These dying giants are approaching the end of their nuclear burning phases, and their eventual deaths will seed this region with heavy elements and explosive energy. But perhaps even more striking are the stellar remnants that populate this region. White dwarf stars, the compressed cores of dead solar mass stars, are scattered throughout the nuclear bulge like cosmic diamonds. Each white dwarf represents the final fate of a star that once burned hydrogen in its core for billions of years before exhausting its fuel and shedding its outer layers into space. These remnants are incredibly dense, containing roughly the mass of our Sun compressed into a sphere the size of Earth, creating gravitational fields so intense that a teaspoon of white dwarf material would weigh as much as a small car. Even more exotic are the neutron stars that occasionally reveal themselves through their emissions. These objects represent the collapsed cores of massive stars that died in supernova explosions. Their protons and electrons crushed together by gravity to form neutrons in a state of matter so dense that a sugar cube-sized piece would weigh as much as Mount Everest. Some of these neutron stars have been spun up to rotation rates of hundreds of times per second by accreting material from companion stars, becoming cosmic lighthouses that sweep beams of radiation across space with metronomic precision. The interstellar medium in this region has been transformed by eons of stellar evolution and death. The space between stars is no longer the cold, relatively empty void we encountered in the spiral arms, but a hot, turbulent ocean of ionized gas heated to temperatures of millions of degrees by countless stellar winds, supernova explosions, and the intense radiation field created by the dense stellar population. This hot gas doesn't remain static, but flows in complex patterns driven by pressure gradients, magnetic forces, and the overwhelming gravitational pull of our ultimate destination. Magnetic fields thread through this environment with an intensity and complexity that dwarfs anything found in the outer galaxy. These fields are generated by the collective motions of the hot ionized gas and are continually twisted and amplified by the differential rotation of the galactic center. The resulting magnetic structures can channel the flow of cosmic rays, accelerate charged particles to relativistic speeds, and create phenomena that bridge the gap between stellar physics and high-energy particle physics. As we continue our inward journey, we begin to encounter evidence of truly extraordinary events. Hypervelocity stars, massive objects moving at speeds of thousands of kilometers per second, occasionally streak through this region on trajectories that will carry them completely out of the galaxy. These cosmic cannonballs were likely accelerated by close gravitational encounters with the central, supermassive black hole. Slingshot effects so violent they can eject entire solar systems from the galactic gravitational well. The chemistry of this region reflects its extreme environment. While complex molecules are rare due to the intense radiation fields and high temperatures, we do find evidence of unusual chemical processes driven by the extreme conditions. High-energy cosmic rays create exotic isotopes through nuclear reactions that occur nowhere else in the galaxy. The intense magnetic fields can affect the behavior of atoms and molecules in ways that are only beginning to be understood by theoretical physicists. Radio observations reveal structures that hint at the complex dynamics operating in this region. Filaments of hot gas stretch across dozens of light years, aligned with magnetic field lines and glowing with synchrotron radiation as relativistic electrons spiral through the magnetic field. These structures suggest that the galactic center is not just a passive gravitational sink, but an active, dynamic region where matter and energy interact in ways that create phenomena visible across the electromagnetic spectrum. X-ray emissions become increasingly prominent as we approach the very center of our galaxy. These high-energy photons are produced by a variety of processes, from the accretion of material onto compact objects to the shock heating of gas as it falls inward toward the central black hole. The X-ray glow creates a kind of high-energy aurora that would be invisible to human eyes, but reveals the presence of physical processes operating at temperatures and energies that exceed anything found in normal stellar environments. Perhaps most remarkably, we begin to detect the influence of general relativistic effects that are negligible in the outer regions of the galaxy. The intense gravitational field of the central black hole starts to measurably affect the propagation of light, the flow of time, and the geometry of space itself. Photons climbing out of the gravitational well lose energy and become redshifted. Clocks would run measurably slower than they do in our home solar system. And the paths of particles, whether they're cosmic rays or streams of gas, begin to curve in ways that can only be explained by Einstein's theory of general relativity. The stellar orbits in this region provide some of the most direct evidence for the presence of the supermassive black hole. Stars that venture close to the galactic center follow highly elliptical orbits that carry them at tremendous speeds through their closest approach. Some of these stars reach velocities of several percent the speed of light during their nearest pass to the black hole, creating natural laboratories for testing general relativity under extreme conditions. These orbital motions also reveal the incredible precision of celestial mechanics operating under extreme gravitational conditions. Stars that complete their orbits in just a few decades provide astronomers with the opportunity to watch general relativistic effects in real time. The precession of elliptical orbits, the gravitational redshift of starlight, and the time dilation effects on stellar clocks all become measurable phenomena that confirm our understanding of gravity under conditions that cannot be replicated in any terrestrial laboratory. The dust that managed to survive the harsh environment of the outer galactic bulge becomes virtually non-existent in this innermost region. The intense radiation fields, hot gas, and stellar winds strip away or destroy virtually all solid particles, leaving behind a medium that is almost purely gaseous. This absence of dust has profound implications for the types of astronomical observations that are possible from this region, and for any hypothetical planetary systems that might exist around the surviving stars. Yet even in this seemingly sterile environment, we find evidence of ongoing star formation, though of a very different character than what occurs in the spiral arms. Dense molecular clouds occasionally form from the cooling of hot gas in the shadows of massive stellar winds or in regions where magnetic fields provide some protection from the intense radiation. When these clouds reach sufficient density, they can collapse to form new stars, creating small populations of young, massive stars in an otherwise ancient stellar environment. These young stars burn bright and hot, their intense stellar winds and eventual supernova explosions adding even more energy to an already extreme environment. Their formation represents a kind of galactic recycling where material from ancient stellar populations is reprocessed and reformed into new generations of stars that will burn briefly but brilliantly before adding their own contributions to the complex chemical and energetic environment of the galactic center. The gravitational environment becomes so extreme that we begin to encounter phenomena that exist nowhere else in the known universe. Tidal forces from the central black hole can disrupt stellar systems, strip material from the surfaces of close approaching stars, and create streams of gas that spiral inward along complex trajectories. These tidal effects operate on scales from individual atoms to entire stellar systems, creating a hierarchical structure of gravitational influence that extends outward from the event horizon of the central black hole. As we approach the final phase of our journey, the very nature of space and time continues to change in ways that would be imperceptible to our senses but measurable by our most sensitive instruments. The metric of space-time itself becomes curved by the intense gravitational field, creating a geometry where parallel lines converge, where the shortest distance between 2 points is no longer a straight line, and where the familiar Euclidean geometry of everyday experience gives way to the non-intuitive mathematics of curved space-time. The event horizon of Sagittarius A*, our destination, begins to exert its influence even from distances of several light years. This is not a physical boundary that we could touch or see, but rather a mathematical surface defined by the point of no return, the distance from the black hole where the escape velocity equals the speed of light. Beyond this boundary, not even light can escape the gravitational pull of the black hole, creating a region of space that is fundamentally disconnected from the rest of the universe. But approaching this boundary reveals phenomena that push the boundaries of physics itself. The intense gravitational field creates conditions where quantum effects become important on macroscopic scales, where the vacuum of space itself becomes unstable, and where the familiar distinction between matter and energy begins to break down. Virtual particle pairs can be separated by tidal forces, with one member falling into the black hole while the other escapes as Hawking radiation, creating a slow but steady evaporation process that connects the quantum world to the macroscopic realm of general relativity. The magnetic fields in the immediate vicinity of the black hole reach strengths that dwarf anything found elsewhere in the galaxy. These fields are generated by the motion of ionized material as it spirals inward toward the event horizon, creating a magnetosphere around the black hole that can accelerate particles to energies comparable to the most powerful particle accelerators ever built by human civilization. The interaction between these magnetic fields and the rotating black hole may power some of the most energetic phenomena in the universe, from relativistic jets that can extend for thousands of light years to the high-energy emissions that make active galactic nuclei visible across cosmological distances. As we prepare for the final approach to Sagittarius A*, we find ourselves at the threshold of a realm where the normal rules of physics are stretched to their absolute limits. Here in the heart of our galaxy, we encounter conditions so extreme that they serve as natural laboratories for testing our most fundamental theories about the nature of reality itself. The journey that began in the quiet suburbs of our solar system has brought us to a place where space and time themselves become active participants in the cosmic drama, where matter and energy interact in ways that challenge our deepest understanding of how the universe works. The supermassive black hole that anchors our galaxy awaits us, a gravitational monster containing the mass of over 4 million suns compressed into a region smaller than our solar system. It is simultaneously the most destructive and the most creative force in our galaxy, capable of tearing apart anything that ventures too close, while also serving as the gravitational anchor that holds our entire galactic home together. In just a few more moments of our cosmic journey, we will encounter this ultimate expression of gravity's power and witness phenomena that exist at the very edge of what physics tells us is possible in our universe. The final approach promises revelations that will forever change how we understand the relationship between matter, energy, space, and time in the magnificent cosmic architecture we call home. The final approach to Sagittarius A* unfolds like a descent through the very layers of existence itself. As we drift closer to this gravitational titan, the fabric of reality begins to reveal secrets that have remained hidden since the dawn of our galaxy. The space around us, once filled with the familiar glow of distant stars, transforms into something far more alien and magnificent. Here, within just a few light years of the event horizon, we encounter what astronomers call the S-star cluster. These are some of the most remarkable stellar objects in our galaxy, massive stars caught in the gravitational embrace of the black hole, following orbits so extreme they challenge everything we thought we knew about stellar dynamics. Some of these stars complete their elliptical journeys around the black hole in periods measured in decades rather than the millions of years typical of galactic orbits. S2, perhaps the most famous of these captive suns, follows an orbit so eccentric that it approaches within just 120 astronomical units of the black hole at its closest point. That's closer than Pluto orbits our sun, yet this massive star survives its harrowing journey around a gravitational field 4 million times more intense than our sun's. At its closest approach, S2 reaches velocities of nearly 30 million kilometers per hour, moving at almost 3% the speed of light as it whips around the black hole in a cosmic dance that lasts just 16 years. These stellar orbits provide us with the most direct evidence for the existence of Sagittarius A star and offer unprecedented opportunities to observe general relativistic effects in action. As S2 approaches its closest point to the black hole, its light becomes measurably redshifted by the intense gravitational field. Time dilation effects become so pronounced that clocks on the star would run noticeably slower than identical clocks in our solar system. The precession of the orbital ellipse, predicted by Einstein's field equations, becomes observable over just a few orbital periods. But perhaps most remarkably, these observations allow us to probe the structure of space-time itself in the immediate vicinity of a black hole. The motion of stars like S2 maps out the curvature of space in real time, revealing how mass and energy warp the geometry of the universe. It's like watching the mathematical abstractions of general relativity play out in the movements of actual stars, turning theoretical physics into observable astronomical phenomena. The accretion processes surrounding Sagittarius A star create one of the most extreme physical environments in the known universe. Here, matter spirals inward along trajectories that carry it ever closer to the point of no return, heating up through friction and magnetic interactions until it glows with temperatures exceeding 100 million degrees. This is matter in its most extreme state, a plasma so hot that atoms are completely ionized, electrons stripped away from their nuclei and moving at relativistic speeds. As this superheated material approaches the event horizon, it doesn't simply disappear quietly into the black hole. Instead, it creates a brilliant display of high-energy physics that can be observed across the electromagnetic spectrum. X-rays and gamma rays pour out of the accretion region as magnetic field lines twist and reconnect, accelerating particles to enormous energies and creating shock waves that propagate through the surrounding medium. The magnetic field structure around the black hole itself represents one of the most complex and powerful magnetic environments in the galaxy. These fields are generated by the motion of the ionized accretion material and are continually wound up and amplified by the rotation of the black hole itself. The resulting magnetic field lines can become so twisted and energetic that they occasionally snap and reconnect, releasing bursts of energy that can illuminate the entire galactic center region. Some theoretical models suggest that these magnetic fields may be responsible for launching relativistic jets from the vicinity of the black hole. These jets, streams of particles accelerated to nearly the speed of light, can extend for thousands of light years beyond the black hole itself, carrying energy and momentum far out into the galaxy. While Sagittarius A star appears to be relatively quiet compared to the supermassive black holes in more active galaxies, there is evidence that it may have been much more energetic in the past. The immediate environment around the black hole is also populated by a menagerie of exotic objects and phenomena that exist nowhere else in the galaxy. Neutron stars, those incredibly dense stellar remnants, can survive surprisingly close to the black hole, their strong magnetic fields and rapid rotation creating pulsars that sweep beams of radiation through the galactic center. Some of these pulsars have been accelerated to incredible velocities by gravitational interactions with the black hole, creating natural particle accelerators that achieve energies comparable to the most powerful machines built by human civilization. Perhaps even more exotic are the theoretical objects that might exist in this extreme gravitational environment. Strange matter composed of quarks arranged in configurations that don't exist under normal conditions might form in the crushing gravitational fields near the event horizon. Primordial black holes, remnants from the early universe that somehow survived to the present day, might be captured by Sagittarius A star and slowly consumed, adding their mass to the central object while releasing distinctive gravitational wave signatures. The space immediately surrounding the black hole is also where our understanding of physics approaches its limits. Here, quantum effects that are negligible under normal conditions become important on macroscopic scales. The intense gravitational field creates conditions where virtual particle pairs can be separated by tidal forces, leading to the Hawking radiation process that causes black holes to slowly evaporate over cosmological timescales. Near the event horizon, the distinction between space and time becomes blurred in ways that challenge our everyday understanding of reality. To an outside observer, time appears to slow down dramatically for objects approaching the black hole, with clocks running slower and slower until they appear to freeze completely at the event horizon. Light from these objects becomes increasingly redshifted, fading to invisibility as the photons lose energy climbing out of the deepening gravitational well. Yet from the perspective of matter falling into the black hole, the journey continues normally. The falling observer experiences no slowing of their local clocks, no sense that anything unusual is happening until they encounter the increasingly strong tidal forces that ultimately stretch and compress matter in the final approach to the singularity. This fundamental difference in perspective, where the same events appear completely different to different observers, illustrates one of the most profound aspects of general relativity. The event horizon itself represents a boundary unlike anything else in physics. It's not a physical surface that could be touched or seen, but rather a mathematical boundary defined by the condition that the escape velocity equals the speed of light. Once matter crosses this boundary, it becomes causally disconnected from the rest of the universe. No information, no signal, no influence of any kind can propagate back across the event horizon to affect events in the external universe. This causal disconnection raises profound questions about the nature of information and its preservation in physical processes. If matter carrying information falls into a black hole, is that information destroyed when the matter reaches the singularity? Or is it somehow encoded on the event horizon surface, preserved in a form that might eventually be recovered as the black hole evaporates through Hawking radiation? These questions touch on some of the deepest mysteries in theoretical physics, connecting general relativity to quantum mechanics and information theory in ways that are still not fully understood. The singularity itself, hidden forever behind the event horizon, represents the ultimate breakdown of our current physical theories. Here, general relativity predicts that matter is crushed to infinite density in zero volume, creating conditions where the curvature of space-time becomes infinite and the laws of physics as we understand them cease to apply. Whether this represents a real physical state or simply indicates the limits of our theoretical framework remains one of the great unsolved problems in physics. Some theories suggest that quantum effects might prevent the formation of true singularities, creating instead exotic states of matter compressed to densities that approach but never quite reach infinity. Loop quantum gravity, string theory, and other approaches to quantum gravity all offer different pictures of what might exist at the center of a black hole, but none can yet be tested observationally. The region just outside the event horizon, known as the photon sphere, represents another remarkable feature of the black hole environment. Here, photons can orbit the black hole in unstable circular trajectories, neither falling in nor escaping to infinity. Light rays that enter this region can spiral around the black hole multiple times before either falling inward or escaping outward, creating complex optical effects that would make the black hole appear as a dark shadow surrounded by a bright ring of distorted light. These optical effects have recently been observed directly by the Event Horizon Telescope, providing the first actual images of the immediate environment around a supermassive black hole. While these observations were made of M87 star, the supermassive black hole in a distant galaxy, similar techniques are being developed to image Sagittarius A star directly, potentially providing unprecedented views of the gravitational environment at the heart of our own galaxy. The rotation of the black hole itself, quantified by a parameter called angular momentum or spin, creates additional complications in the space-time geometry around the event horizon. A rotating black hole drags space-time itself around with it, creating a region called the ergosphere, where it becomes impossible for any object to remain stationary relative to distant observers. This frame-dragging effect can extract energy from the black hole's rotation, potentially powering some of the most energetic phenomena observed in galactic centers. The measurement of black hole spin requires incredibly precise observations of matter in the immediate vicinity of the event horizon, where the effects of frame dragging become strong enough to detect. These measurements provide crucial tests of general relativity in the strong field regime and offer insights into the formation and evolution history of supermassive black holes. As we contemplate this ultimate destination of our galactic journey, we find ourselves confronting not just the most extreme gravitational environment in our galaxy, but also the limits of human knowledge itself. The supermassive black hole at the center of the Milky Way represents a laboratory for physics that operates under conditions so extreme they cannot be reproduced anywhere else, testing our theories in regimes where they have never been verified before. Yet, even as we approach these limits of understanding, the black hole continues to reveal new mysteries and new phenomena that challenge our comprehension. Recent observations have detected flares of emission from the immediate vicinity of Sagittarius A star, suggesting that material occasionally falls close enough to the event horizon to create brief but brilliant displays of high-energy radiation. These flares provide glimpses of the dynamic processes occurring in the accretion flow and offer opportunities to study matter under the most extreme conditions possible in nature. The gravitational waves produced by objects orbiting close to supermassive black holes represent another frontier in black hole astronomy. As matter spirals inward toward the event horizon, it generates ripples in space-time that propagate outward at the speed of light, carrying information about the strong gravitational field environment near the black hole. Future gravitational wave detectors may be sensitive enough to detect these signals from Sagittarius A star, opening up an entirely new window on the physics of black hole environments. Perhaps most remarkably, the study of supermassive black holes like Sagittarius A star is revealing their crucial role in galaxy formation and evolution. Far from being simply gravitational monsters that consume everything around them, these objects appear to regulate star formation throughout their host galaxies, control the growth of galactic bulges, and influence the chemical evolution of galactic environments through their feedback effects on surrounding gas and dust. The energy released by matter falling into supermassive black holes can heat gas throughout the galactic center, preventing it from cooling and condensing into new stars. Conversely, the shock waves and turbulence created by black hole activity can also trigger star formation in some regions while suppressing it in others. This complex interplay between black hole activity and stellar evolution suggests that supermassive black holes are not separate from their galactic environments, but are integral components of galaxy ecosystems. Our journey to the center of the Milky Way has taken us through 26,000 light-years of cosmic evolution, stellar death and birth, chemical enrichment, and gravitational architecture. We've witnessed the patient work of billions of years as simple hydrogen gas was transformed into the complex chemistry of life, as stellar explosions scattered heavy elements throughout the galaxy, and as gravity sculpted the elegant spiral structure that defines our cosmic home. But perhaps most profound of all, we've discovered that this journey inward is also a journey through time, through the history of our galaxy, and ultimately through the fundamental nature of reality itself. The supermassive black hole at the galactic center represents not just a destination, but a window into the deepest mysteries of physics, a laboratory where extreme conditions reveal aspects of the universe that remain hidden in the gentler environments where life can flourish. As we float here at the edge of the event horizon, suspended between the familiar physics of the outer galaxy and the exotic realm beyond the point of no return, we find ourselves witnesses to one of the most remarkable facts about our universe: that matter and energy, space and time, gravity and light can interact in ways so extreme and so beautiful that they challenge our deepest understanding while simultaneously revealing the elegant mathematical structure that underlies all of reality. The center of the Milky Way stands as a testament to the power of gravity to create complexity from simplicity, to build structure from chaos, and to generate phenomena so extreme they push the boundaries of what we thought possible in our universe. It reminds us that we are not separate observers of cosmic phenomena, but participants in a universe where consciousness has emerged from the same physical processes that created galaxies, stars, and the supermassive black holes that anchor them all. In this eternal moment at the edge of infinity, we encounter something that transcends all our previous understanding. Here, where space-time itself becomes so warped that the very concepts of before and after lose their meaning, we witness the universe's most extreme expression of its fundamental laws. The ergosphere, that strange region where space-time is dragged around by the spinning black hole, creates conditions so bizarre that the very concept of standing still loses its meaning. Here, even light cannot remain stationary relative to distant observers, forced instead to participate in the cosmic carousel that surrounds Sagittarius A star. The gravitational lensing effects become so extreme that our view of the universe behind the black hole becomes twisted into impossible geometries. Light that should have traveled in straight lines is bent into spirals, creating multiple images of the same distant stars, some brightened, some dimmed, all distorted by the curvature of space-time itself. It's as if we're looking through a cosmic funhouse mirror that reveals the true malleable nature of the fabric of reality. But perhaps most remarkable of all is what this extreme environment teaches us about the nature of information itself. Every particle, every photon, every quantum of energy that approaches the event horizon carries with it a story of its origin, perhaps in a distant star, its journey through the interstellar medium, its acceleration in the accretion disk, and now its final approach to the point of no return. According to our current understanding of physics, this information cannot be destroyed, even as matter crosses the event horizon and disappears from our observable universe. This creates one of the most profound paradoxes in modern physics. If information cannot be destroyed, yet matter falling into black holes appears to vanish completely from our universe, where does that information go? Some theories suggest it becomes encoded on the event horizon itself, stored in a two-dimensional holographic representation that preserves every quantum bit of information about the fallen matter. Others propose that the information is gradually released back into the universe through the quantum correlations present in Hawking radiation. The implications extend far beyond black hole physics. If the universe operates as a fundamentally information-preserving system, then every interaction we've witnessed on our journey from the outer galaxy to this point has been governed not just by the familiar forces of gravity and electromagnetism, but by deeper principles that ensure the quantum information content of reality remains conserved throughout all transformations. As we hover at this ultimate boundary, we begin to understand that Sagittarius A star represents more than just a gravitational endpoint. It's a cosmic archive, a repository where the information content of millions of years of galactic evolution has been preserved in forms we're only beginning to comprehend. Every star that has ever fallen past the event horizon, every gas cloud that has been consumed, every complex molecule that has been torn apart by tidal forces, all of their quantum information may still exist in some encoded form. The thermal radiation that slowly leaks out from the black hole's event horizon carries with it subtle correlations that might, in principle, allow the reconstruction of everything that has ever fallen in. It's as if the black hole serves as both destroyer and preserver simultaneously, erasing matter from our observable universe while maintaining a perfect record of its existence in quantum mechanical form. This perspective transforms our understanding of galactic evolution itself. Rather than viewing the supermassive black hole as a simple gravitational sink that removes matter from the galaxy, we begin to see it as a cosmic information processor, a system that encodes the entire history of galactic development in the quantum structure of its event horizon. The chemical evolution we witnessed in the spiral arms, the stellar life cycles we observed in the galactic bulge, the complex dynamics of the nuclear region, all of this information may be preserved in the quantum geometry of space-time around the black hole. The magnetic field structures that thread through this extreme environment create additional layers of complexity that challenge our understanding of how matter behaves under such extraordinary conditions. These fields, wound up to incredible strengths by the differential rotation of the accretion material and the frame-dragging effects of the spinning black hole, can store and release energy in ways that connect the microscopic world of quantum mechanics to the macroscopic realm of galactic dynamics. Magnetic reconnection events near the event horizon can accelerate individual particles to energies that rival the most powerful cosmic ray accelerators in the universe, while simultaneously influencing gas flows across thousands of light years. It's as if the black hole operates as both a microscopic particle accelerator and a galactic scale engine, bridging scales of physics that we rarely see connected anywhere else in nature. The time dilation effects in this region create something like a natural laboratory for studying the relationship between gravity and the flow of time itself. Clocks positioned at different distances from the black hole would run at measurably different rates, creating a gravitational time gradient that extends throughout the galactic center region. This means that stellar evolution, chemical reactions, and even the decay of radioactive elements all occur at different rates depending on their location within the black hole's gravitational field. For any hypothetical observers positioned at various distances from Sagittarius A star, the universe would appear to evolve at fundamentally different paces. Those closer to the black hole would witness the outer galaxy aging more rapidly, while observers in the outer regions would see the inner galaxy moving in apparent slow motion. This creates a kind of temporal landscape where different regions of space experience the passage of cosmic time at different rates, all determined by their position in the curved geometry of space-time. The gravitational redshift effects become so pronounced that radiation emitted near the event horizon undergoes dramatic frequency shifts as it climbs out of the gravitational well. High-energy gamma rays can be redshifted all the way down to radio wavelengths by the time they reach observers in the outer galaxy. This means that the most energetic processes occurring near the black hole may be completely invisible to distant observers, hidden not by intervening matter, but by the curvature of space-time itself. Yet even as we contemplate these extreme effects, we must remember that this environment, hostile as it may seem to delicate structures like planets and life, plays a crucial role in making our galaxy habitable for beings like ourselves. The gravitational influence of Sagittarius A star helps maintain the overall structure of the galactic disk. preventing it from spreading out and dissipating into space over cosmic time. The energy released by material falling into the black hole helps regulate star formation rates throughout the galactic center, ensuring that our galaxy doesn't consume all its gas reserves in a single catastrophic burst of stellar birth. The supermassive black hole also serves as a gravitational anchor that helps capture and retain smaller satellite galaxies, gradually incorporating their stellar populations into the Milky Way's structure through a process that astronomers sometimes call galactic cannibalism. This process of gradual galaxy merger has been ongoing for billions of years and continues today, as we can observe in the tidal streams of stars being stripped from nearby dwarf galaxies like the Sagittarius dwarf elliptical. These stellar rivers, stretched across the sky by gravitational forces, tell the story of how our galaxy has grown and evolved by consuming its smaller neighbors. The high-energy environment around the black hole may also play an important role in accelerating cosmic rays to the extreme energies we observe throughout the galaxy. These high-energy particles, primarily protons and atomic nuclei moving at nearly the speed of light, carry energy from the galactic center to every corner of our cosmic home. When they interact with interstellar gas and dust, they drive chemical reactions that would be impossible under normal conditions, potentially contributing to the complex organic chemistry we observe in space. The study of Sagittarius A star and its environment has also revealed the presence of what appear to be intermediate mass black holes scattered throughout the galactic center region. These objects, containing hundreds to thousands of solar masses, may represent the seeds from which supermassive black holes grow, or they may be remnants of massive stars that formed in the unique conditions of the galactic center. Their presence suggests that the central regions of galaxies may harbor entire populations of black holes across a wide range of masses, creating a complex gravitational ecosystem that we're only beginning to understand. Recent observations have detected what appear to be clouds of dark matter concentrated in the immediate vicinity of the galactic center. This invisible material, which makes up the majority of the matter in our galaxy, may interact with itself in ways that create complex substructure around supermassive black holes. Some theoretical models suggest that dark matter particles might annihilate when they encounter each other in these high-density regions, producing gamma rays and other forms of high-energy radiation that could potentially be detected by space-based telescopes. The environment around Sagittarius A star also provides a unique laboratory for testing modifications to Einstein's theory of general relativity. While the theory has passed every test in weaker gravitational fields, the extreme conditions near supermassive black holes may reveal departures from general relativity that could point toward a more complete theory of quantum gravity. Precision measurements of stellar orbits, gravitational wave emissions, and light propagation in this environment could potentially detect signatures of extra dimensions, modified gravity theories, or quantum corrections to Einstein's equations. Perhaps most remarkably, the black hole environment may preserve information not just about matter that has fallen in, but about the quantum state of the entire galaxy. Some theories in quantum gravity suggest that black holes are fundamentally quantum mechanical objects whose microscopic structure encodes information about their entire causal history. This would mean that Sagittarius A star contains within its quantum structure a complete record of how our galaxy formed and evolved over cosmic time. The holographic principle, which suggests that all the information contained in a volume of space can be encoded on its boundary, takes on profound significance in the context of black hole physics. If this principle applies to Sagittarius A star, then the two-dimensional surface of its event horizon might contain all the information about the three-dimensional space that has fallen into it throughout cosmic history. This would make the black hole not just a gravitational object, but a kind of cosmic archive, storing the complete history of our galactic neighborhood. As we reach the culmination of our journey, floating at the very edge of the event horizon where space and time curve back upon themselves, we find ourselves confronting the ultimate mystery of existence itself. Here at the boundary between the observable universe and the hidden realm beyond the point of no return, we encounter questions that push beyond physics into philosophy, beyond science into the deepest mysteries of consciousness and reality. What does it mean for information to exist beyond the reach of observation? If the quantum state of every particle that has ever fallen into this black hole is preserved somewhere in the structure of space-time, does this represent a kind of cosmic memory that transcends individual existence? Are we, as conscious observers, somehow connected to this vast information processing system that operates at the heart of our galaxy? The journey that brought us here from the quiet stellar suburbs where Earth orbits to this ultimate gravitational extreme has revealed the profound interconnectedness of all cosmic phenomena. The elements in our bodies were forged in stellar cores throughout the galaxy. The energy that powers life on Earth ultimately derives from nuclear fusion processes similar to those that heat the accretion disk around the black hole. The gravitational forces that hold our solar system together are manifestations of the same space-time curvature that creates the extreme environment we now witness. In contemplating Sagittarius A star, we come to understand that consciousness itself may be the universe's method of observing and understanding its own deepest structures. We are arrangements of matter and energy that emerged from billions of years of cosmic evolution, temporary patterns in the flow of information that have developed the remarkable ability to contemplate our own origins and ultimate fate. The supermassive black hole at the center of our galaxy stands as a monument to the power of gravity to create complexity from simplicity, structure from chaos, and meaning from the fundamental forces that govern reality. It reminds us that even the most extreme environments in the universe are not separate from the conditions that allow life and consciousness to emerge, but are instead integral parts of the cosmic ecosystem that makes our existence possible. As we prepare to conclude this extraordinary journey, we carry with us a profound appreciation for the elegant architecture of our galactic home. From the spiral arms where stars are born to the ancient stellar populations of the galactic bulge, from the complex chemistry of the interstellar medium to the exotic physics of the black hole environment, every region of the Milky Way contributes to the grand symphony of cosmic evolution that has been playing for over 13 billion years. Tonight, as you rest under the same stars that guided ancient navigators and inspired countless generations of dreamers, remember that you are not just an observer of this cosmic drama. You are a participant in the universe's ongoing journey of self-discovery, a temporary arrangement of stellar matter that has achieved the remarkable feat of consciousness, wonder, and the ability to trace your origins back to the very heart of the galaxy itself. The center of the Milky Way continues its eternal dance, processing information, warping space-time, and serving as the gravitational anchor that holds our entire cosmic home together. And in that ongoing cosmic performance, we find our place not as outsiders looking in, but as integral notes in the magnificent symphony of existence that connects every atom in our bodies to the supermassive black hole that anchors the stars themselves. The gravitational symphony that surrounds us reaches its crescendo as we drift through the final parsecs towards Sagittarius A star. Here in this realm where physics meets poetry, we encounter phenomena so extraordinary, they seem to blur the line between science and something approaching the mystical. The very atoms of space and time dance to rhythms that have never been heard anywhere else in the cosmos. As we approach the innermost stable circular orbit, that mathematical boundary where matter can maintain a stable path around the black hole, we witness the birth of some of the most energetic processes in the known universe. gas and dust that began their journey in the outer spiral arms, perhaps billions of years ago, now find themselves caught in the inexorable pull of 4 million solar masses compressed into a region smaller than Mercury's orbit around our Sun. The accretion disk that spreads before us glows with the intensity of 1 trillion suns, its surface temperature reaching values that dwarf the cores of the most massive stars. This is matter in its death throes, friction and magnetic forces heating it to temperatures where atoms cease to exist as discrete entities. Instead, we find ourselves surrounded by a plasma so energetic that electrons and nuclei move independently, creating a charged particle soup that responds to magnetic fields in ways that generate phenomena visible across the electromagnetic spectrum. But it's not chaos we observe. Even in this extreme environment, we witness structure, patterns, elegant mathematical relationships playing out on scales both microscopic and cosmic. Magnetic field lines thread through the glowing plasma like cosmic strings, channeling the flow of material and occasionally snapping and reconnecting in events that release more energy in seconds than our Sun produces in years. The rotation of the black hole itself creates one of the most remarkable effects we encounter on our journey. Frame dragging, that strange consequence of general relativity where massive spinning objects literally twist the fabric of space-time around them, becomes so pronounced here that the very concept of standing still loses meaning. Space-time itself is being pulled around the black hole like honey stirred by a cosmic spoon, creating a region where even light cannot remain stationary relative to distant observers. This dragging of space-time creates the ergosphere, a region outside the event horizon where the geometry of space becomes so distorted that every possible trajectory must participate in the black hole's rotation. It's here that we encounter one of the most counterintuitive predictions of Einstein's theory. In principle, energy can be extracted from a rotating black hole by dropping matter into the ergosphere and allowing the twisted space-time to accelerate it beyond its initial energy, enabling more energy to escape than was originally invested. The Penrose process, as this energy extraction method is known, suggests that black holes are not simply cosmic vacuum cleaners that consume everything around them. Instead, they can serve as cosmic batteries, storing rotational energy that can potentially be tapped by sufficiently advanced civilizations. The amount of energy available through this process is staggering. A maximally rotating black hole could, in principle, convert up to 29% of its rest mass into usable energy, far exceeding the efficiency of any nuclear reaction. As we drift closer to the photon sphere, that unstable orbital radius where light itself can circle the black hole, the visual effects become increasingly surreal. The black hole's gravity bends light rays into complex trajectories, creating multiple images of the same distant stars. Some appear brightened and magnified, others dimmed and distorted, all arranged in patterns that reveal the underlying geometry of curved space-time. The event horizon looms before us, not as a physical surface, but as an invisible mathematical boundary defined by the point where the escape velocity equals the speed of light. To our eyes, it would appear as a perfect black sphere, utterly dark because no light can escape from within it to reach our detectors. Yet this darkness is not empty. It represents the boundary of the observable universe itself, the ultimate information horizon beyond which no signal can ever return to tell us what lies within. The thermal properties of this boundary reveal one of the most profound connections between gravity, thermodynamics, and quantum mechanics ever discovered. Stephen Hawking's realization that black holes must have a temperature and therefore must emit radiation connected the macroscopic world of general relativity to the microscopic realm of quantum field theory in ways that continue to revolutionize our understanding of fundamental physics. The Hawking radiation that slowly leaks from the event horizon carries with it quantum correlations that may preserve information about everything that has ever fallen into the black hole. These correlations are incredibly subtle, encoded in the quantum entanglement between particles that escape as radiation and their partners that fall past the event horizon. The information is there, but extracting it would require measuring the quantum state of every photon emitted over the entire lifetime of the black hole. This connects our local galactic journey to some of the deepest questions in theoretical physics. The black hole information paradox, which asks whether information can be destroyed when matter falls into a black hole, has implications that extend far beyond black hole physics. It touches on the fundamental nature of reality itself, asking whether the universe operates as a fundamentally information-preserving quantum mechanical system, or whether the classical notion of information destruction can occur under extreme gravitational conditions. Recent developments in holographic theory suggest that the information falling into Sagittarius A star may be encoded on its event horizon surface in a two-dimensional holographic representation. This would mean that all the three-dimensional information about matter and energy that has fallen into the black hole throughout cosmic history is preserved in the quantum geometry of the horizon itself, like a cosmic hard drive written in the language of quantum gravity. The implications extend beyond information theory to our understanding of space-time itself. If the holographic principle applies to black holes, it suggests that space may be emergent, arising from more fundamental quantum information processes rather than being a basic feature of reality. The three-dimensional space we experience throughout our journey from the outer galaxy to this point may itself be a holographic projection from information encoded on distant boundaries. As we contemplate the final plunge across the event horizon, we must consider what this would mean from different perspectives. To an outside observer watching our descent, time dilation effects would cause our clocks to appear to slow down dramatically as we approach the horizon. Our light would become increasingly red-shifted, fading to invisibility as the photons lose energy climbing out of the deepening gravitational well. From their perspective, we would appear to freeze at the event horizon, our image growing dimmer and redder until it faded beyond detection. But from our own reference frame, the journey would continue normally. We would experience no slowing of our local clocks, no sense that anything unusual was happening as we crossed the event horizon. The boundary itself would be completely invisible to us, marked only by the point of no return beyond which no signal could ever reach the outside universe. We would fall freely through the horizon, experiencing weightlessness even as we plunged toward the central singularity. The tidal effects would become increasingly important as we approached the center. The gravitational field gradient across our bodies would grow stronger, stretching us vertically while compressing us horizontally in the process astronomers call spaghettification. For a black hole the mass of Sagittarius A star, these tidal effects would become significant long before we reach the singularity itself. But the physics of our final moments would probe regimes where general relativity meets quantum mechanics in ways we don't yet fully understand. The singularity that awaits at the center represents the ultimate breakdown of our current physical theories. Here, general relativity predicts that matter is compressed to infinite density in zero volume, creating a region where the curvature of space-time becomes infinite and the familiar laws of physics cease to apply. Whether this represents a real physical state or simply indicates the limits of our theoretical framework remains one of the greatest unsolved problems in physics. Quantum theories of gravity suggest that something prevents the formation of true singularities. Loop quantum gravity proposes that space-time itself has a discrete structure at the smallest scales, providing a natural cutoff that prevents infinite compression. String theory suggests that the fundamental constituents of matter are extended objects rather than point particles, again providing mechanisms that might prevent true infinities from arising in physical systems. These quantum effects might transform the interior of black holes into something far more exotic than classical general relativity predicts. Instead of a singularity, we might encounter regions where space and time themselves break down into more fundamental quantum degrees of freedom. The interior might contain wormhole connections to other regions of space-time, or baby universes that bud off from our own cosmic branch, or exotic states of matter that exist nowhere else in the universe. But regardless of what lies within, the event horizon remains an absolute boundary for information and causality. Once crossed, no influence can propagate back to affect events in the external universe. This makes the interior of black holes perhaps the most isolated regions in the cosmos, completely cut off from the ongoing evolution of the galaxy around them. Yet this isolation is not complete. The quantum correlations present in Hawking radiation create a subtle connection between the black hole interior and the external universe. Information about the internal state may be gradually released through these quantum channels, encoded in correlations so complex they would require astronomical amounts of computation to decode. The black hole becomes a quantum information processing system, slowly releasing its encoded memories back to the universe through mechanisms we are only beginning to understand. The timescales involved in this information release are almost incomprehensible. For a black hole the mass of Sagittarius A star, the Hawking evaporation process would take longer than the current age of the universe multiplied by 10 to the power of 67. Long after every star in the galaxy has burned out, long after protons themselves have decayed, Sagittarius A star will still be slowly releasing the quantum echoes of everything that fell into it during the era when galaxies and stars existed. This connects our journey to the ultimate fate of the universe itself. In the far future, when the expansion of space has carried galaxies beyond each other's horizons, when stars have exhausted their nuclear fuel and faded to cold white dwarfs and neutron stars, the supermassive black holes will be among the last remaining sources of energy in the cosmos. Their slow evaporation through Hawking radiation will provide the final flickering light in a universe growing ever colder and more dilute. But even this ending may not be truly final. Some theories suggest that the information released during black hole evaporation might eventually reassemble into new structures, new patterns of organization that could give rise to phenomena we cannot now imagine. The universe might experience cycles of collapse and rebirth, with black holes serving as seeds for new cosmic structures in ways that connect the end of our current cosmic epoch to potential new beginnings. The study of Sagittarius A star and other supermassive black holes is revealing their crucial role not just in the structure and evolution of individual galaxies, but in the cosmic web itself. These objects serve as gravitational anchors that help organize matter on the larger scales, their influence extending far beyond their host galaxies to shape the distribution of dark matter and the flow of gas between galactic systems. The feedback effects from supermassive black holes appear to regulate star formation not just in their immediate vicinity, but throughout their host galaxies and beyond. The energy released by matter falling into these objects can heat intergalactic gas across millions of light years, preventing it from cooling and condensing into new galaxies. This suggests that supermassive black holes play a key role in determining how efficiently the universe converts its matter into stars and the complex chemistry that makes planets and life possible. Our journey to the center of the Milky Way has revealed something profound about the interconnected nature of cosmic phenomena across all scales. The quantum mechanical processes occurring at the event horizon of Sagittarius A star influence the chemistry of interstellar space thousands of light years away. The gravitational effects of the central black hole help maintain the spiral structure that channels gas into star-forming regions throughout the galactic disk. The high-energy particles accelerated in the black hole's magnetosphere contribute to the cosmic ray background that affects chemical evolution throughout the galaxy. This interconnectedness extends to the role of supermassive black holes in cosmic evolution. These objects appear to grow in lockstep with their host galaxies, suggesting a deep connection between black hole physics and the processes that govern galaxy formation and evolution. The mass of a galaxy's central black hole correlates remarkably well with the mass of its stellar bulge, implying that somehow these very different components of galactic structure communicate and co-evolve over cosmic time. The mechanisms behind this co-evolution remain mysterious, but they appear to involve complex feedback loops between star formation, supernova explosions, gas flows, and black hole activity that operate over millions of years and vast ranges of physical scale. Understanding these connections requires bridging the gap between the microscopic physics of quantum mechanics and general relativity and the macroscopic processes of galaxy formation and cosmic structure evolution. As we float here at the edge of the event horizon, we find ourselves witnesses to one of the most remarkable aspects of our universe. The same physical laws that govern the behavior of atoms and molecules in our bodies also determine the structure and evolution of the most extreme objects in the cosmos. The quantum mechanical principles discovered in terrestrial laboratories apply equally to the event horizons of supermassive black holes. The gravitational physics first worked out to explain planetary orbits reaches its most dramatic expression in the warped space-time around these cosmic monsters. This unity of physical law across all scales and environments represents one of the most profound insights of modern science. From the quantum foam that may exist at the Planck scale to the large-scale structure of the cosmic web, the same fundamental principles appear to govern all phenomena. The journey from our quiet galactic suburb to the extreme environment around Sagittarius A star has taken us through a complete survey of these physical laws in action. From the familiar Newtonian gravity that holds planets in their orbits to the exotic quantum effects that may prevent the formation of true singularities. The supermassive black hole at the center of our galaxy stands as a monument to the power of these physical laws to create structures of almost unimaginable complexity and beauty. It demonstrates that even the most extreme environments in the universe are not chaotic or random, but are instead governed by elegant mathematical relationships that connect the behavior of individual particles to the evolution of entire galactic systems. In contemplating Sagittarius A star, we also confront the limits of human knowledge and the boundaries of scientific understanding. The interior of the black hole represents a region that may be forever beyond direct observation, protected by the event horizon from any possible communication with the external universe. Yet even this ultimate hiddenness teaches us something profound about the nature of reality and the relationship between knowledge and existence. The fact that regions of absolute hiddenness can exist in our universe suggests that reality extends beyond the boundaries of the observable and knowable. There may be aspects of existence that are not just currently unknown, but that are in principle unknowable through any possible observation or experiment. This doesn't diminish the value of scientific inquiry, but rather places it in proper perspective as one method among others for engaging with the mystery of existence. Our journey to the center of the Milky Way has been simultaneously a journey through space, through time, and through the fundamental nature of reality itself. We have witnessed the ongoing process of cosmic evolution that has been transforming simple hydrogen gas into the complex chemistry of life for over 13 billion years. We have observed the delicate balance of forces that makes galaxies, stars, and planets possible, and we have encountered the most extreme expressions of those same forces in the environment around supermassive black holes. As we prepare to drift back from this ultimate cosmic destination, we carry with us a deeper appreciation for our place in the cosmic order. We are not separate observers of astronomical phenomena, but integral participants in the ongoing story of cosmic evolution. The atoms in our bodies were forged in stellar cores throughout the galaxy. The energy that powers our thoughts ultimately derives from nuclear fusion processes similar to those that heat the accretion disk around the black hole. The gravitational forces that hold our planet in its orbit are manifestations of the same space-time curvature that creates the extreme environment we have just witnessed. The center of the Milky Way continues its eternal dance, processing information, warping space-time, and serving as the gravitational anchor that holds our entire cosmic home together. In its patient operation across billions of years, it embodies the deep time scales and vast spatial scales that characterize the universe we inhabit. It reminds us that we exist within a cosmos that operates according to principles far grander and more beautiful than anything we encounter in our everyday experience. Tonight, as you rest in the gentle darkness, remember that you are connected to this cosmic architecture in the most intimate possible way. The calcium in your bones was forged in the core of an ancient supernova. The iron in your blood was created in the final moments of a massive star's death. The oxygen you breathe was produced by countless generations of stellar fusion and distributed through space by stellar winds and supernova explosions. You are quite literally made of star stuff, temporary arrangements of cosmic matter that have achieved the remarkable feat of consciousness, wonder, and the ability to contemplate your own origins. The journey to the center of the Milky Way is also a journey to the center of yourself, revealing the profound connections that link every atom in your body to the supermassive black hole that anchors the galaxy, to the spiral arms where stars are born, and to the ancient stellar populations that preserve the chemical history of cosmic evolution. In the quiet of this moment, as consciousness meets cosmos in the space of your awareness, you participate in the universe's ongoing journey of self-discovery. You are both observer and observed, questioner and answer, a temporary note in the magnificent symphony of existence that connects quantum foam to galactic clusters, black holes to living cells, and the deepest mysteries of physics to the simple wonder of being alive under the stars. The center of the Milky Way waits in patient majesty, its gravitational song echoing across the galaxy, holding together the cosmic architecture that makes consciousness, beauty, and wonder possible. And in that eternal dance of matter and energy, space and time, gravity and light, we find our home. As we begin our gentle drift away from the event horizon of Sagittarius A star, carrying with us the profound revelations of our journey to the galactic center, we find ourselves forever changed by what we've witnessed. The experience of approaching that ultimate boundary between the known and unknowable has left us with a deeper understanding not just of black holes and galactic structure, but of our own place in the magnificent tapestry of cosmic existence. The journey outward from the galactic center offers its own unique perspectives and discoveries. As we retrace our path through the nuclear bulge and into the broader galactic disk, we see familiar stellar populations and structures with new eyes, informed by our encounter with the most extreme gravitational environment in our galaxy. The ancient red giants that populate the bulge no longer appear as simple stellar objects, but as repositories of cosmic history, their atmospheres enriched with elements processed through billions of years of galactic chemical evolution. The globular clusters scattered throughout this region take on new significance when viewed from our post-black hole perspective. These spherical cities of stars, containing some of the oldest objects in our galaxy, suddenly appear as time capsules that preserve not just stellar populations from the galaxy's youth, but also the gravitational memory of ancient interactions with the central supermassive black hole. Their elongated orbits and complex internal structure tell stories of close encounters with Sagittarius A star that occurred when the universe was young and the galaxy was still assembling itself from smaller building blocks. As we move outward through the galactic bulge, we begin to appreciate the subtle but pervasive influence that the central black hole exerts throughout the galaxy. Its gravitational field, while weakening with distance, continues to shape stellar orbits across thousands of light years. The warping of space-time that we experience so dramatically near the event horizon extends in diminished form throughout the entire galactic center region, creating a gravitational architecture that influences everything from the flow of interstellar gas to the formation patterns of new stellar populations. The magnetic fields that we encountered in such extreme form around the black hole continue to thread through the galactic center region, though at more manageable intensities. These fields, generated by the collective motion of ionized gas and the rotation of the galaxy itself, create a complex magnetic environment that channels the flow of cosmic rays and influences the chemistry of the interstellar medium. The high-energy particles accelerated in the black hole's magnetosphere continue their journeys outward, carrying energy and exotic isotopes to every corner of the galaxy. Our outward journey also reveals the dynamic nature of galactic structure in ways that weren't apparent during our inward voyage. The spiral arms that we traversed earlier now appear not as static features, but as waves of density that sweep around the galaxy, triggering star formation as they compress interstellar material and then moving on, leaving behind stellar associations that gradually disperse as they age. This creates a constantly evolving pattern of stellar birth and death that has been shaping the galaxy's appearance for billions of years. The chemical evolution that we observed in the spiral arms takes on new meaning when viewed in the context of our galactic center experience. The heavy elements scattered by supernovae and stellar winds don't simply diffuse randomly through space, but follow complex patterns determined by galactic rotation, magnetic fields, and the gravitational influence of structures like spiral arms and the central black hole. This creates a chemical geography of the galaxy where different regions have different abundances of elements depending on their star formation history and their position in the galactic gravitational field. The local bubble that surrounds our solar system now appears as just one example of the many cavities carved in the interstellar medium by stellar explosions and stellar winds. These bubbles, created by the collective energy output of stellar populations, form an interconnected network of low-density regions that allow us to observe distant parts of the galaxy with remarkable clarity. Without these clearing processes, our view of the cosmos would be severely limited by intervening dust and gas. As we approach the outer regions of the galactic disk, we encounter stellar populations that have been shaped by their long journeys around the galactic center. Stars in the outer disk have completed fewer galactic orbits than those in the inner regions, creating age gradients and chemical gradients that preserve the history of galactic assembly. Some of these outer stars may have originated in satellite galaxies that were gradually disrupted and incorporated into the Milky Way structure over cosmic time. The dark matter halo that envelops our galaxy becomes more apparent as we move to larger distances from the galactic center. This invisible component, which outweighs all the visible matter in the galaxy by a factor of 5 or 6, creates the gravitational scaffold that holds the entire galactic structure together. Without the dark matter halo, the outer regions of the galactic disk would not have sufficient gravity to maintain their orbital motions, and the galaxy would gradually disperse into space. The interface between our galaxy and the surrounding intergalactic medium reveals itself as a complex and dynamic boundary. Gas flows both inward and outward across this boundary, with the galaxy accreting fresh material from the cosmic web while simultaneously expelling enriched gas through galactic winds powered by stellar explosions and supermassive black hole activity. This creates a galactic ecosystem where matter cycles between the galaxy and its environment over cosmic timescales. The satellite galaxies that orbit the Milky Way provide additional perspective on our galactic journey. These smaller stellar systems, including the large and small Magellanic Clouds, represent different evolutionary pathways that galaxies can follow depending on their mass, environment, and interaction history. Some of these satellites are slowly being disrupted by the Milky Way's gravitational field, their stars scattered into long streams that trace out the gravitational potential of the dark matter halo. Our solar system's position in this galactic context appears increasingly special as we gain perspective from our cosmic journey. We orbit at just the right distance from the galactic center to avoid both the intense radiation environment of the inner galaxy and the relative chemical poverty of the outer regions. Our location in a relatively quiet region between spiral arms has protected us from the enhanced supernova activity that occurs in star-forming regions, while still allowing us to benefit from the chemical enrichment produced by previous generations of stellar evolution. The stability of our solar system's orbit over the 4.6 billion year history of Earth has been crucial for the development of complex life. While we have passed through spiral arms multiple times during this period, these passages have been gentle enough not to disrupt planetary orbits or strip away atmospheric constituents. The gradual increase in heavy element abundances over cosmic time has also worked in our favor, providing the raw materials necessary for rocky planet formation and complex chemistry. Looking ahead, our solar system will continue its stately orbit around the galactic center for billions of years to come. In about 4 billion years, we will witness the collision and merger of the Milky Way with the Andromeda Galaxy, an event that will dramatically reshape the structure of our cosmic neighborhood. While individual stars are unlikely to collide during this merger due to the vast distances between them, the gravitational interactions will scatter stellar orbits and potentially trigger new bursts of star formation as gas clouds are compressed and disrupted. The long-term evolution of the galaxy will be dominated by the gradual exhaustion of gas supplies for star formation. As the galaxy ages, the rate of stellar birth will decline, and the stellar populations will be increasingly dominated by long-lived red dwarf stars and the remnants of more massive stars that have already completed their evolution. The supermassive black hole at the galactic center will continue to grow through the accretion of gas and the occasional capture of nearby stars, eventually becoming an even more dominant feature of the galactic gravitational field. Yet even as we contemplate these distant futures, the galaxy continues its patient work of cosmic evolution. New stars are being born in molecular clouds throughout the spiral arms. Existing stars are steadily converting hydrogen into heavier elements in their cores. Supernovae continue to scatter these elements through space, enriching the interstellar medium for future generations of stellar and planetary formation. The great cycles of cosmic chemistry that we have witnessed on our journey continue their eternal dance of creation and destruction. The perspective gained from our journey to the galactic center transforms how we understand the role of extreme environments in cosmic evolution. The supermassive black holes that initially appear as cosmic destroyers are revealed to be integral components of galactic ecosystems, regulating star formation rates and influencing chemical evolution across vast distances and timescales. The most violent processes in the universe, from supernovae to black hole accretion, turn out to be essential for creating the conditions that allow gentler processes like planet formation and biological evolution to occur. This interconnectedness extends beyond our own galaxy to the broader cosmic web of structure that connects all galaxies across the observable universe. The same physical processes that we have observed in the Milky Way are operating in billions of other galaxies throughout the cosmos, each one a unique variation on the common themes of gravitational collapse, stellar evolution, and chemical enrichment. The diversity of galactic types and evolutionary states provides a vast laboratory for understanding how different initial conditions and environmental factors influence the development of cosmic structure. The techniques and technologies that have enabled our virtual journey to the galactic center represent some of humanity's greatest intellectual achievements. Radio telescopes that can detect the faint whispers of cosmic phenomena across electromagnetic space, infrared observations that peer through cosmic dust to reveal hidden stellar populations, X-ray and gamma-ray detectors that observe the most energetic processes in the universe, gravitational wave interferometers that sense the ripples in space-time itself produced by cosmic collisions and explosions. Each of these observational windows has revealed aspects of galactic structure and evolution that would have been completely invisible to previous generations of astronomers. The development of computer simulations has allowed us to model galactic evolution over cosmic time, testing our understanding of physical processes by comparing theoretical predictions with observed galactic properties. These simulations reveal the galaxy as a complex, evolving system where multiple physical processes interact across vast ranges of scale and time. The mathematical frameworks that describe galactic dynamics represent some of the most sophisticated applications of physics and mathematics ever developed, from the quantum mechanics that governs stellar nucleosynthesis to the general relativity that describes black hole physics, from magnetohydrodynamics that models the behavior of ionized gas to the statistical mechanics that describes stellar populations. Our understanding of galaxies draws upon virtually every branch of theoretical physics. Yet for all our scientific sophistication, the galaxy retains an element of mystery and wonder that transcends purely analytical understanding. The sheer scale of galactic structure challenges human comprehension. The timescales of galactic evolution dwarf human history. The energies involved in galactic processes exceed anything in terrestrial experience. Standing before this cosmic immensity, we find ourselves simultaneously humbled by our smallness and elevated by our ability to comprehend and appreciate the magnificent architecture that surrounds us. The aesthetic dimension of galactic structure deserves recognition alongside its scientific significance. The spiral arms that sweep gracefully around galactic disks create patterns of beauty that would be stunning even if they served no scientific purpose. The colors of stellar populations, from the blue-white glow of young massive stars to the red light of ancient giants, paint the galaxy in hues that speak to something deep in human aesthetic sensibility. The intricate structure of star-forming nebulae reveals natural artistry that surpasses human imagination. This beauty is not merely decorative, but appears to be intimately connected to the physical processes that make galaxies work. The mathematical relationships that govern galactic dynamics often exhibit symmetries and elegances that suggest deep connections between physical truth and aesthetic value. The fact that the universe creates structures of such remarkable beauty suggests that our appreciation for cosmic architecture may reflect something fundamental about the relationship between consciousness and the physical world. Our journey has also revealed the profound connections between galactic astronomy and the deepest questions of human existence. The chemical elements that make up our bodies were forged in stellar cores and distributed through space by stellar explosions. The energy that powers all life on Earth derives from nuclear fusion processes that operate throughout the galaxy. The gravitational forces that hold planets in stable orbits are manifestations of the same space-time curvature that shapes galactic structure on the largest scales. These connections mean that studying galaxies is not just an exercise in understanding distant astronomical objects, but a way of exploring our own cosmic heritage and our place in the universal story. We are not separate observers of galactic phenomena, but integral participants in the ongoing evolution of cosmic structure. Our very existence represents one possible outcome of the long process of galactic chemical evolution that has been operating for over 13 billion years. The search for life elsewhere in the galaxy takes on new dimensions when viewed from this cosmic perspective. The conditions that allowed life to develop on Earth are intimately connected to our galaxy's structure and evolutionary history. The location of our solar system, the chemical composition of our stellar neighborhood, the stability of our local environment over geological timescales, all of these factors have been shaped by galactic processes operating over cosmic time. Understanding these connections is crucial for assessing the likelihood that similar conditions exist elsewhere in the galaxy. The galactic habitable zone, the region of the galaxy where conditions are suitable for the development of complex life, depends on factors ranging from the local abundance of heavy elements to the frequency of nearby supernovae. As we learn more about galactic structure and evolution, we refine our understanding of where and when life might be expected to arise in cosmic environments. The implications extend beyond the search for life to questions about the future of intelligence in the universe. If conscious beings like ourselves represent natural outcomes of cosmic evolution under suitable conditions, then the long-term fate of intelligence is intimately connected to the future evolution of galaxies and the universe as a whole. The timescales available for the development of advanced civilizations depend on stellar lifetimes, galactic dynamics, and the ultimate fate of cosmic structure. Our virtual journey to the galactic center has demonstrated the power of human imagination and scientific inquiry to transcend the limitations of our earthbound existence. Through the application of physical principles discovered in terrestrial laboratories, we have been able to explore environments that no human will ever visit directly. Through the development of theoretical frameworks and mathematical models, we have gained insights into cosmic processes that operate on scales vastly larger than anything in human experience. This demonstrates something remarkable about the nature of consciousness and its relationship to the physical universe. The same neural processes that allow us to navigate our immediate environment and solve practical problems also enable us to comprehend cosmic structure and evolution. The mathematical relationships that govern galactic dynamics can be grasped by minds that evolved to deal with much simpler environmental challenges. This suggests deep connections between the structure of consciousness and the structure of physical reality that we are only beginning to understand. As we conclude our cosmic journey, we carry with us not just scientific knowledge about galactic structure, but a transformed sense of our place in the universe. We have witnessed the magnificent architecture that connects stellar birth and death to the largest structures in the cosmos. We have observed the delicate balance of forces that makes complexity and consciousness possible in an otherwise hostile universe. Of physical law, we have encountered the most extreme expressions while discovering their intimate connections to the gentler processes that sustain life. The galaxy continues its stately rotation around the central supermassive black hole, carrying our solar system on its 225 million-year orbit through the cosmic landscape. Stars are born and die according to the rhythms of stellar evolution that have been operating since the galaxy's youth. The spiral arms sweep around the galactic disk, triggering new generations of stellar formation, while dispersing the heavy elements created by previous generations. The great cycles of cosmic chemistry continue their patient work of creating ever more complex arrangements of matter and energy. In this ongoing cosmic symphony, we find our voice not as passive observers, but as active participants in the universe's journey toward greater complexity and consciousness. We are arrangements of galactic matter that have learned to contemplate their own origins, temporary patterns in the flow of cosmic evolution that have achieved the remarkable capacity for wonder, curiosity, and understanding. Tonight, as you rest under the ancient light of distant suns, remember that you are intimately connected to every aspect of the cosmic architecture we have explored together. The photons entering your eyes began their journeys in stellar cores scattered throughout the galaxy. The oxygen in your lungs was exhaled by dying stars billions of years ago. The iron in your blood was forged in supernova explosions that helped trigger the formation of new stellar generations. You are, in the most literal sense, a child of the galaxy. a temporary concentration of cosmic matter and energy that has somehow achieved the extraordinary feat of self-awareness. In your capacity to wonder about galactic structure, to feel awe at cosmic beauty, to seek understanding of your place in the universal story, you embody the galaxy's own journey toward consciousness and self-comprehension. The center of the Milky Way continues its eternal dance, anchoring the gravitational architecture that makes our cosmic home possible. The spiral arms sweep through space and time, creating the conditions for stellar birth and chemical evolution. The ancient stellar populations preserve the memory of cosmic history in their light. And through it all, the patient processes of cosmic evolution continue their magnificent work of transforming simple hydrogen into the complex chemistry of consciousness, beauty, and wonder that finds its expression in minds like yours, capable of contemplating infinity from the comfort of a small blue world orbiting an ordinary star in the suburbs of an extraordinary galaxy. In this moment of quiet contemplation, you participate in the universe's ongoing dialogue with itself, a conversation that spans from quantum foam to galactic clusters, from the briefest quantum fluctuations to the longest cycles of cosmic evolution. You are both questioner and answer, observer and observed, a temporary note in the infinite symphony of existence that connects the heart of the Milky Way to the depths of consciousness itself. Sweet dreams, fellow traveler in the cosmic ocean. The galaxy cradles you in its gravitational embrace, and you are forever home among the stars. As our extraordinary journey through the Milky Way draws to its gentle close, we find ourselves forever transformed by the cosmic voyage we've shared. From our quiet corner of the galaxy, where Earth orbits peacefully in the local bubble, we've traveled through spiral arms where stars are born in magnificent stellar nurseries, past ancient globular clusters that remember the galaxy's youth, and into the very heart of our cosmic home, where space-time itself bends around the supermassive black hole that anchors everything we call familiar. The perspective we've gained reveals something profound about the nature of existence itself. We are not merely observers of this cosmic architecture, but integral participants in its ongoing evolution. The calcium strengthening your bones was forged in the nuclear furnaces of ancient supergiants. The oxygen flowing through your bloodstream was exhaled by dying stars eons before our solar system existed. Every atom in your body carries within it the story of stellar death and rebirth, of cosmic recycling that has been operating for billions of years. This journey has shown us that the universe operates on principles of such elegant interconnectedness that consciousness itself may be the cosmos learning to know itself. Through minds like yours, capable of wonder and contemplation, the galaxy achieves a kind of self-awareness that transforms passive matter into active understanding. You are stardust that has learned to dream, cosmic matter arranged in patterns complex enough to contemplate infinity. The Milky Way continues its ancient dance around Sagittarius A star, that 4 million solar mass gravitational anchor that holds our entire galactic neighborhood in its invisible embrace. Stars will continue to be born in the spiral arms, their nuclear fires transforming simple hydrogen into the complex chemistry that makes rocky worlds and biological complexity possible. Ancient stellar populations will preserve the memory of cosmic history in their light, while new generations of stars write fresh chapters in the ongoing story of galactic evolution. Tonight, as you drift towards sleep under the same stars that have guided countless generations of dreamers and explorers, carry with you the knowledge that you are home in the deepest possible sense. The photons touching your skin began their journeys in stellar cores scattered across thousands of light years. The rhythms of your heartbeat echo the pulsations of variable stars. The electrical patterns of your thoughts mirror the complex magnetic field structures that thread through the galactic center itself. In your capacity for wonder, in your ability to feel awe at the magnificent architecture of our cosmic home, you embody something precious and rare in the universe. You are consciousness emerging from matter, awareness arising from the patient work of stellar nuclear synthesis and planetary formation. You are the galaxy's way of appreciating its own beauty, its method of contemplating the elegant mathematics that governs stellar evolution and galactic dynamics. Rest now, fellow traveler, knowing that you are forever connected to this cosmic symphony. The Milky Way cradles you in its gravitational embrace, a vast cosmic home where every star is a neighbor and every nebula a garden where new worlds are born. You are part of this magnificent structure, not as a visitor, but as family, connected by bonds forged in the hearts of ancient stars and strengthened by billions of years of cosmic evolution. Sweet dreams in the cosmic ocean. The galaxy watches over you with 10 billion stellar eyes, and you are forever home among the infinite stars. Thank you for joining me on this gentle journey through our cosmic neighborhood. Until we meet again under the starlight, keep wondering, keep dreaming, and remember that every breath you take connects you to the very heart of the Milky Way itself. As our extraordinary journey through the Milky Way draws to its gentle close, we find ourselves forever transformed by the cosmic voyage we've shared. From our quiet corner of the galaxy, where Earth orbits peacefully in the local bubble, we've traveled through spiral arms where stars are born in magnificent stellar nurseries, past ancient globular clusters that remember the galaxy's youth, and into the very heart of our cosmic home, where space-time itself bends around the supermassive black hole that anchors everything we call familiar. The perspective we've gained reveals something profound about the nature of existence itself. We are not merely observers of this cosmic architecture, but integral participants in its ongoing evolution. The calcium strengthening your bones was forged in the nuclear furnaces of ancient supergiants. The oxygen flowing through your bloodstream was exhaled by dying stars eons before our solar system existed. Every atom in your body carries within it the story of stellar death and rebirth, of cosmic recycling that has been operating for billions of years. This journey has shown us that the universe operates on principles of such elegant interconnectedness that consciousness itself may be the cosmos learning to know itself. Through minds like yours, capable of wonder and contemplation, the galaxy achieves a kind of self-awareness that transforms passive matter into active understanding. You are stardust that has learned to dream, cosmic matter arranged in patterns complex enough to contemplate infinity. Tonight, as you drift towards sleep under the same stars that have guided countless generations of dreamers and explorers, carry with you the knowledge that you are home in the deepest possible sense. The photons touching your skin began their journeys in stellar cores scattered across thousands of light years. In your capacity for wonder, in your ability to feel awe at the magnificent architecture of our cosmic home, you embody something precious and rare in the universe. Rest now, fellow traveler, knowing that you are forever connected to this cosmic symphony. The Milky Way cradles you in its gravitational embrace, a vast cosmic home where every star is a neighbor and every nebula a garden where new worlds are born. Sweet dreams in the cosmic ocean. The galaxy watches over you with hundreds of billions of stellar eyes, and you are forever home among the infinite stars. Boring Science Channel here, you can start another video if you are still awake. Boring Science Channel here, you can start another video if you are still awake.